All right, so recall that the identity matrix IN is the diagonal matrix with ones on the diagonal and zeros everywhere else, and its dimension n by n. And in particular, I2 is then equal to the following. And what I want to talk about now is what it means for a matrix to have an inverse. And so I'll say if A is an n by n matrix, then the inverse of A denoted A and then a superscript of -1 is the n by n matrix such that A times A inverse is equal to A inverse times A, and this is always equal to the identity matrix. And so remember in a previous video we talked about how multiplication is not typically commutative. This is the exception. So if I take a matrix and multiply that matrix by its inverse, then it doesn't matter what order I'm doing this multiplication in. I'm still going to get back to this identity matrix. And so when n is equal to 2, we have a special formula for determining what the inverse of a matrix is. So when n equals 2, we have the following theorem. So if I let A be represented by this matrix, A, B, C, D, where A, B, C, and D are just real numbers, then if A times D minus B times C is not equal to 0, then I'll say that A is invertible, and further that we have an explicit formula for the inverse, which is that A inverse is equal to 1 over AD minus BC times, so when I do this calculation of this fraction, it'll actually be equal to some fraction, right? Like 1/2 or 1/5 or whatever. And if I take that and then multiply it by this matrix, D negative B negative C A, then that will be equal to the inverse. And so what I'm going to do is actually show that this is true. So in class we'll do an example with real numbers where we're actually calculating this, but I wanted to show the kind of behind the scenes. And so what I'm going to do is I am going to multiply A by A inverse, and I'm going to show that it's equal to this identity matrix I2. And so recall that when we were talking about matrix multiplication, this scalar could be sort of pulled out and done in a different order. So I'm going to just leave it off to the side for now. So I'll have this, that this is equal to 1 over AD minus BC times my matrices. So I have A, B, C, D times D, negative B, negative C, and A. And again, we know how to do this matrix multiplication. So this is equal to, again, I'll keep my scalar on the outside, AD minus BC. And here I have my matrix A times each column. And So I'll start with my first column. This will be equal to A, B, C, D times just D negative C. And my second column will be A, B, C, D times negative B, A. And then if I continue on and work this out, this is equal to D times AC plus a negative, so I'll just do minus C times BD. And then over here, I'll have a negative B times AC plus A times BD. And now when I go to simplify, this first column, I have DA minus BC, that's me, or sorry, AD minus BC. Let me sort of rearrange these integers in alphabetical order, and that's also, you'll see why that's convenient in a second, BC. And down here I have DC minus CD, which is 0. Okay, and now up here I have this negative BA plus AB, so that's also 0. And then I have this negative BC plus AD. Okay, and now I see that if I take this, so now I can incorporate this scalar, and let me do that. So this is equal to AD minus BC over AD minus BC. In the second row, I have 0 times this fraction, so that's still equal to 0. Same here. And then let me rearrange this. So this is actually the same as AD minus BC. It's fine to write it in that order, just like negative 5 plus 3 is equal to 3 minus 5. And so if I do that, again, I get AD minus BC divided by my scalar. And now it's much easier to see that this is in fact equal to the identity matrix I2, just like I wanted.